Greetings and salutations, everybody. This is Jacob. Okay, so how do we go about solving this problem? I can't wrap my gray matter around it, you say. Well, my friend, get in line. You're not the only one that can't make heads or tails of this beast of a problem. But don't worry, I'm going to break down everything so that even a 5-year-old can understand it. So, let's get this show on the road, shall we? What's our strategy going to be to maximize the probability we'll hire the absolute best applicant out of n applicants? I know the problem states out of 9 applicants, but we'll tackle the general case first. So in order to maximize this probability, we'll have to automatically reject the first batch of applicants. Let's call this group K-1. So if someone comes along that's better than the best in K-1, then we stop at that applicant. That's the applicant that we'll choose, in other words. So when we're presented with an applicant, we can either select them on the spot or reject them on the spot and keep going. But if we reject them, then we can't come back to them later. They're rejected for good. Okay, now let's give some definitions. N is the total number of applicants. K-1 is the automatically rejected group. K is where the real interviewing starts. And I is the chronological order in which the applicant is being interviewed. I meaning ith, 4th, 5th, 6th, etc. So now our objective is to find where this k number is with respect to n in order to maximize this probability. So let's try to come up with a formula for this probability. So the probability of finding the top applicant is the probability that the first applicant is best and is selected, plus the probability the second applicant is best and is selected, all up to n, correct? Of course, the probability that the first applicant is selected is 0, of course, because K-1 has to have at least one person in there, and they're automatically rejected, like we said. So let's put that all together. So this probability is this sum right here, which is from I equals 1 to n, of the probability that I is selected and I is the best applicant. The intersection of these two events, in other words. So these two events are not independent events. One is independent and the other one is dependent on the other. Which one is which? Actually, you can make whichever you want as the independent event, but in this case we'll choose I is the best as the independent event and I is selected as the dependent event. Okay, so what's the formula for the independent and dependent events? Do you remember? It's probability of A intersection B equals probability of A times the probability of B given that A has occurred, where A is the independent event and B is the dependent event. So far so good? Okay, so now let's go back to our formula, this sum here, from 1 to n of the probability I is best times the probability that I is selected given that I is the best. So what's the probability that I is the best? It's 1 over n, correct? So now we have the sum from 1 to n of 1 over n times probability of I is selected given that I is best. So what is the probability that I is selected given that I is best? It's the same as the probability of nobody and I-1 was selected. In other words, nobody else can be selected prior to I. Make sense? So what does that mean? It means that the first of this group here, the I-1 group, the group that were interviewed before the ith applicant, the first of this group, the absolute best of this group, is in the K-1 group. In other words, if the top dog of I-1 was outside of the K-1 group, then he or she would have been selected. Make sense? So what is this probability? It's simply this ratio here, K-1 over I-1. Correct? Does what I'm saying make sense so far? I hope it does. Okay, moving on. So now we have sum from 1 to n of 1 over n times K-1 over I-1. Okay, so since the K-1 are automatically rejected, then we further break down the sum. So now we have the sum from 1 to K-1, which is 0, plus the sum from K to n of 1 over n times K-1 over I-1. The K-1 over n, we bring it out of the second sum because it's a constant. And so now we have K-1 over n times the sum from K to n of 1 over I-1. Okay, now we have a formula. Now what do we do? Let's solve the general case first. The ratio of the rejects over the total number of applicants, in other words, K-1 over n, This ratio converges to a specific number as n gets larger and larger. So when n is large, k minus 1 is approximately k, or n minus 1 is approximately n, correct? And this sum here is approximately the integral from k to n of 1 over x minus 1 dx. Since the sum and the integral represent the same thing, the area under the curve, so now we have Pn of k approximately k minus 1 over n times the integral from k to n of 1 over x minus 1 dx. And we integrate this and we get k minus 1 over n times ln of x minus 1, and you plug in the endpoints. So we get this expression here. So now we've eliminated the sum. We have a function of the probability in terms of k, where n is a constant. So to maximize this function, we take the derivative and equate it to 0. So now we have this expression here, and we do the calculations and all the algebraic manipulations, and we end up with k minus 1 over n equals 1 over e, which is approximately 37%. And so for the case where n equals 9, we just test out the k minus 1 over 9 values that are close to 37%. So when k equals 4, we have k minus 1 over n equals 1/3, 33.3%. That's pretty close to 37%. So we test that value out, which is P9 of 4 equals 3 over 9 times the sum from 4 to 9 of 1 over I minus 1, which is approximately 40.6%. And 4 over 9 is 44.4%. Let's test out this value as well. So probability of 9 of 5 equals 4 over 9 times sum from 5 to 9 of 1 over I minus 1, which is approximately 39.31%. So that's our answer basically, k equals 4, which means our optimal strategy is to reject the first 3 applicants and to choose the first candidate that is better than these 3 applicants, and the optimal probability is 40.6%. And that's your answer, 40.6%, which is an intuitive answer if you ask me. But wait, we're not done yet. Now comes the main event of this video, my friends. If you want to give a lovely variant of this problem a shot, then stick around, because you're in for a real treat, my friends. Oh yes. The variant is as follows. Okay, so how do we go about solving this problem? It looks bewildering. Well, this variant is a little trickier and more complicated than the previous one. Besides finding the optimal number of rejects, or k minus 1, you have to find the optimal of what I call S. Namely, we automatically reject the first k minus 1, and we stop at the first candidate that is better than the best in k minus 1, like we did before. But also at some point, we'll call this point S. From the S candidate and onward, we start settling for a second best. In other words, we're compromising for I equals S and onwards in order to maximize the probability that we'll select the top 2 candidates. So how do we formulate this mathematically? So our probability is this, Pn of k and s equals sum from 1 to n of probability I is selected and I is top 2. The same thing we did before, only difference being we're searching for the top 2 now instead of the best. And since the k minus 1 group is already rejected by default, we have Pn of k and s equals the sum from 1 to k minus 1 of 0. This sum is 0. Plus the sum from k to n of the probability that I is selected and I is the top 2. Okay, so now here is where the fun starts. Here's where the fireworks are unleashed, my friends. Oh yes. So this sum right here, we're going to have to break it down further and introduce s into the equation. And we have Pn of k and s equals the sum from k to s minus 1 of the probability that I is selected and I is top 2, plus the sum from s to n of the probability that I is selected and I is top 2. Make sense so far? So the first sum, we're going to have to break that one down further as well, and you'll see why in a minute. So now we have Pn of k and s equals the sum from k to s minus 1 of the probability that I is selected and I is the best, plus the probability that I is selected and I is second, plus the sum from s to n of the probability that I is selected and I is top 2. So now we use the formula for independent and dependent events like we did before, and we get Pn of k and s equals the sum from k to s minus 1 of the probability of I is best times the probability that I is selected given that I is best, plus the probability that I is second times the probability that I is selected and I is second, plus the sum from S to N of the probability that I is selected and I is top 2. This probability here in the first sum is the same as before, 1 over n times k minus 1 over I minus 1. We bring the k minus 1 over n out of the sum because it's a constant, and hence the first sum is the exact expression like the first part of the video. The only difference is we're summing to s minus 1. Okay, so the second sum now, the probability that I is second is just 1 over n, and we bring that out of the sum because it's a constant. But what about this one? What about the probability that I is selected given that I is second? What's this probability? It's the probability that all those other I minus 1 candidates before the second one is interviewed, all these candidates don't get selected, times the probability that the best candidate is behind the second best in chronological order. In other words, the best is in this section here. So why is that? Because if the best candidate is interviewed before the second best, then he or she will be the one who will be selected. And if the best is in k minus 1, then obviously the second best won't be selected. Because remember, we haven't started compromising yet. Here, we're still searching for the best candidate. So the best candidate has to be behind the second one. So this probability is the best in I minus 1 is in k minus 1 times the probability that the best is behind the second best. And this is k minus 1 over I minus 1 times the ratio of these two sections here. This section is n minus I, and this section is the entirety of the set of the applicants, which is n minus I over n. So the second sum is, after we bring out the constants, is k minus 1 over n squared times the sum from k to s minus 1 of n minus I over I minus 1. Correct? Makes sense so far? So let's go now to the last sum. This is where we start compromising. So we break this down further as the sum from S to N of the probability that I is top 2 times the probability that I is selected given that I is top 2. So the probability that I is top 2 is what? 2 over N, correct? And we bring that out of the sum, and we have this expression here now. So what is this dependent probability? Now we're at the trickiest part of the formula, my friends. So pay good attention here. Let's look at this diagram here. The probability that I is selected, given that I is top 2, is this basically. The probability that the first of S minus 1 is in K minus 1, times the probability that the first and the second of this section here, the I minus 1 section, is in S minus 1. So where the heck did this come from, you ask? Since we started compromising now S minus 1 is the new measuring stick, my friends. The new k minus 1, if you will. So in order for the ith applicant to be selected, the first plus the second of I minus 1 has to be in the new measuring stick, which is S minus 1, times the probability that the best in S minus 1 is in K minus 1. In other words, the first S minus 1, we're playing by different rules, so we have to multiply these two probabilities. Make sense so far? I hope it does. So this probability here is the ratio of these two intervals, which is k minus 1 over s minus 1. And this one here is the probability that the first of I minus 1 is in s minus 1, times the probability that the second of I minus 1 is in s minus 1. And the probability that the first of I minus 1 is in s minus 1 is the ratio of these two intervals, s minus 1 over I minus 1. And the probability that the second of I minus 1 is in s minus 1 is, now the first of I minus 1 is already taking up a slot in s minus 1, as you see here. So you subtract 1 from s minus 1, so now the interval is s minus 2. You subtract from I minus 1 as well, and you have s minus 2 over I minus 2. It's the same thing like when you're drawing aces from a card of decks. Each time you subtract 1 from the numerator and the denominator, because you're drawing without replacement. So far we have 2 over n times the sum from s to n of k minus 1 over s minus 1 times s minus 1 over I minus 1 times s minus 2 over I minus 2. And the s minus 1's cancel out, and we bring out the constants, and we have 2 times k minus 1 times s minus 2 over n times the sum from s to n of 1 over I minus 1 times I minus 2. So putting all this together, So far we have Pn of k and s equals this formula here. This long expression for k equal to or higher than 2, and s is bigger than k. And for s equals k, for that specific case, we have this formula here because the first two sums are undefined in this special case. So what do we do now? We're going to have to plug all the values for k and s, unfortunately, because solving the general case of n is close to impossible in closed form. It involves solving equations involving x's and ln of x's, and that's against the spirit of the problem because numerical methods will be needed to solve equations like that. So we'll only solve the case of n equals 9. So we plug our values, k from 2 to say 7, and s from 3 to 9. And so here's a table base for the various values of k and s. And so according to this table base, the k and s that gives the highest probability is k equals 4 and s equals 7. So putting this all together, the optimal strategy in order to maximize the probability that we'll select the top 2 candidates is to reject the first 3 applicants and then start compromising when we get to the 7th applicant. And the maximum probability is approximately 63.2%. And that's your answer. 63.2% probability. That's an intuitive answer, if you ask me. I mean, intuitively, it makes sense that you'll start compromising at approximately 2/3 of the way through the entirety of the candidates. Wow. Just wow, you guys. What a problem. This problem is no joke. It's famous for a reason, my friends. I have to admit this problem really kicked my teeth in. It took me days of grueling work to come up with these formulas and to wrap my head around this problem in general. This really made my brain bleed, my friends. Making this video, the whole process of it felt more like writing a dissertation or a thesis. So I got a small taste of what those math PhD candidates are going through. Math research is a grueling work. It'll make you go bonkers. That's why those PhD thesis advisors recommend to not work on just one specific problem. Because if you put all your eggs in one basket, then you paint yourself in a corner. If you get stuck on that problem, you're screwed, basically. So yeah, I'm going off on a tangent a bit. But this particular problem, man, it's fascinating. It's considered the gateway problem of the probability subfield that's called optimal stopping theory. It's a mathematical field that deals with coming up with an optimal strategy to do something, of knowing when to stop in order to yield maximum results. And this problem is a prime example of that. I mean, this problem is no joke. I sunk a lot of time in this problem. The hardest video I made on this channel so far. Even harder than that on pursuit curves. This one was much harder than that. Calculating each k and s value was grueling work, but I didn't want to back down, I had already sunk a lot of time on this problem. I didn't want to just quit and go on a different problem. In for a penny, in for a pound, as the saying goes. That's not how we do things on this channel anyway. We don't just up and quit just because going gets tough. There will be no tucking the tail between the legs on this channel, my friends. Oh no, not on my watch. We solve problems or we die trying. But this problem will skyrocket your understanding of probability. I've always had trouble with probability. I didn't have the intuitive grasp of it like I do with geometry, physics, calculus, algebra, and all those other fields. But working on this problem really skyrocketed my understanding of it as well. And I think I managed to break it down so that even a 5-year-old can understand it. Oh yes. So yeah, I hope you like this puzzle. Let me know in the comments what you think. If you found it difficult, if you solved it another way. As always, shoot a puzzle suggestion my way. I'm more than happy to showcase a puzzle that you suggested. And some of you have already suggested a puzzle. They're in the pipeline, don't worry about it. I haven't forgotten about them. So that's pretty much it, my friends. Take care, you guys, and I'll see you in the next video. Bye-bye.